Hello and welcome to part 1 of Dev Maths and Statistics Refresher Course, Lecture 5. The main focus of today's lecture is optimization, and before that we need to look at differentials, which are used in this theory. But first of all, I'm going to have a look at integration, which some of the lecturers have asked me to include in the course because you may meet it in certain topics this year. So, open the first section, restarts Maple, load the plot commands. I'll start with an example, which is we're producing something and you know that the marginal cost of producing another unit of output Q is given by this equation. So in the past I've given you a cost function, that's the total cost function, and we've derived the marginal cost function by differentiating. Now I'm going to tell you that the marginal cost function is this, but I don't know the cost function, so how can I work out the cost function? So maybe pause the video, just jot down what you think the total cost function would be if this is the marginal cost function. Okay, hopefully you've paused that, so let's have a look at what I've put down at least here for the answer. So because we know that the marginal cost function is the derivative of the total cost function, we simply have to find something which, when you differentiate, will give us this. So that's what we're doing here. So if I want to get 6q squared, I have to start with q cubed, and it's going to have to be 2 because 3 times 2 will give me 6. Here I need to get 14q, so if I start with 7q squared, negative 7q squared, that will work. To get this I need 350q and so on, so that's it. So what we've done is we reversed the process of differentiating, because we differentiate this, we get this. We reverse that to get back from here to here. So what we have done, we have integrated the marginal cost function. So integration is simply the opposite of differentiation. Fine, so it's fairly simple. Here's the word almost, because it's only almost. Because there is a complication, which maybe you already know about, but I have to make sure that you recognize this, that suppose that we start with this function that I put here. If we differentiate this, then we get the thing which we want. Differentiate, you get that, fine. Therefore, if I start with this one here and integrate it, I should get back to this one here. So if differentiate this, get to here, therefore integrate this, we get back to here because it's the opposite. But what if I start with this function instead? If I differentiate this one, I will get this one. Therefore, if I start with this and integrate, what I should get is back to here, because it's the opposite. So starting from this should go to here, because this differentiated goes to here. But what if I start with this? If I differentiate this, then I get to this here. So if I integrate this, I should get back to this one. So unfortunately, the integration of this could give us many, many different results, because there are many, many different things which can differentiate and give us the thing which I just deleted, this one here. So unfortunately, there's no unique answer. So when we integrate this one thing, we have to allow for all these different possibilities. So when we integrate this, we say that we get this plus, it could be k or m or c. C is very common, it's just a constant number. Because when we differentiate this again, whatever this constant number is will disappear. So when you integrate, you never know what that number could have been you're starting with. Even back in this example here, I don't know if I should have a plus 10, minus 50, and so there could be some number here, so I have to put plus c. And c is called the constant of integration. And it's essential to remember that that could be there. It could be positive, negative, could be anything. So that's the slight complication with integration, because it's not well defined as differentiation is. Okay, a few remarks on notation. This famous notation you would have seen before. This means you integrate the function x with respect to x. So as in the partial differentiation situation, in the real world there are many, many variables going on. So this dx is here to make it clear which one is varying here, which one are we integrating, just in case there are other variables around. So that's the one, that's what we showed. And to tie up this link between differentiation and integration, we have this rule here, and this rule goes under the very grand title of the fundamental theorem of calculus. The fundamental theorem of calculus is that if you have any function, a big F, if there is a function big F, so you differentiate big F by dx, you get the function small f. So small f is the derivative of big F. Then by definition, the integral of small f must be that original function plus or minus some constant. To specify exactly what this value of c is, we need some more information. So I'll give you a couple of examples of what I mean by that. Continuing that example above, suppose we know that in this situation where I had the marginal cost function, I also know that if I produce 10 units, it's going to cost me 5,000. Well, in that case, I can complete it because when I integrated the cost function, I got this, but I did not know the value of c. But now with the extra information, I can say, okay, let me substitute 10 units into here. So if you put 10 into here, you have 4,800. And then plus c must be equal to the cost of 5,000 for making that. And then we can realize, okay, c must be 200. So the real answer to the cost function was 2q cubed minus 7q squared plus 350q plus 200. So now we have enough information to find the exact answer. And the last thing I'll do in this short video is just to look at another example of this. Let's say someone like Makonde in southern Tanzania are producing beautiful carvings. And to model this in a simple way, and again, if you're looking at the impact of different factors on this person's output, there'll be many things to bear in mind, but let's just stick with one thing. So let's say the output of carvings depends only on labour time. So maybe they have enough wood and so on. But just labour time is the thing that determines how much they produce. Suppose we know that the marginal productivity of this craftsman's labour time is 20 over 1 plus L. This kind of makes sense because as they work more and more, this will tend to go down because they're getting tired. So their marginal productivity is falling with more time. And also another quite reasonable assumption is if you don't do any work, at least work on the carvings, then you produce nothing, which seems reasonable. What's the exact form of production function Q of L, the total production function? Well, let's write down what we've got so far. We've got this for the, one fell swoop. we know that this is the marginal productivity time. So what we're going to do is we're going to integrate the marginal productivity. So integrate that with respect to L. And it comes to log, and because we know that when you differentiate a log, you're going to get 1 over 1 plus L. Because if you imagine differentiating this, you practice it, if you differentiate this, it will become 1 over 1 plus L. Then you have to multiply by the derivative of this according to the chain rule, but the derivative of this is 1, so there's no effect there. So this becomes 20 over 1 plus L, so it is indeed equal to this. But this is only one candidate, it could be plus 50, minus 50, anything, so you have to remember the constants. But we also have some further detail, which is that in this total cost function, sorry, total output function, if the person doesn't do any work on the carving stage, he has to go to the fields or something instead, then we know that the quantity produced by 0 is 0. So we substitute in 0 for L here. 20 times log of 1. Log of 1 is 0, so 0 plus c is equal to 0, so c must be 0. So in this case, the constant of integration actually is just 0. So the production function is just 20 log brackets 1 plus L. So one use of integration is if for some reason you have the marginal function, which sometimes you do get from output data from factories or econometric estimation, okay, when we start varying the output or the purchases, how much does that cost us, that extra bit? Then you can work backwards by integration to get the overall total cost or total product, total cost or yes, total product by integrating. But you have to bear in mind there could be a function, a constant, and often the constant is to do with your fixed costs. Okay, so in the next part of this, I'll go on to look at an important concept, which is the way that integration is connected to area. But for now, thanks for watching.